In this short video, we're going to work out some examples where we find the absolute maximum and minimum function value over a closed region. So let's start with some review from Calculus 1. In Calculus 1, we found the absolute max and min over a closed interval using the extreme value theorem, which just says that if you have a continuous function over a closed interval, then it attains its absolute maximum and absolute minimum on that interval. And let's just work out an example to refresh our memories. We'd like to find the absolute maximum and absolute minimum of the function f of x equals sine of x minus 1/2 x on the closed interval from negative pi over 2 to pi. So our strategy was to first find any critical numbers. So we'll take the derivative, set it equal to 0, and solve. Well, we'll get to cosine of x equals 1/2. And in the interval, negative pi over 2 to pi, the solutions to cosine of x equals 1/2 are x equals negative pi over 3 and x equals positive pi over 3. And then what we did is we said, okay, let's go over all of our critical numbers and all of the endpoints, so all those x values, evaluate them using our given function, and then amongst those, we're going to pick the largest one, that's our absolute max, the smallest one is the absolute min. So the absolute max occurs at x equals pi over 3. It's about 0.342. The exact value is root 3 over 2 minus pi over 6. And the absolute min is negative pi over 2, and that occurs at the endpoint where x equals pi. Now we want to remember this strategy because we're going to be using this as part of a larger strategy with functions of two variables. Now note that we never cared about what type of critical number we had. We didn't care if negative pi over 3 was a local min or a local max, or if pi over 3 correspond to a local min or local max. With this method, we just find all the function values, pick the largest one to be the absolute max, and the smallest one will be the absolute min. So now we have an extreme value theorem for functions of two variables. If you have a continuous function on a closed region R, then f is going to attain its absolute maximum and absolute minimum on that region. So here's an example. We'd like to find the absolute maximum and absolute minimum of the function f of x comma y is x squared plus 2y squared minus 2xy minus 6x plus 4y over the closed rectangle 0, 8 by negative 2, 2. Now this is a shorthand notation, and we're going to use this a lot later on in the course. And really what this means is it's an interval, an x interval cross a y interval. So really it means all ordered pairs where the x coordinate goes between 0 and 8, the y coordinate goes between negative 2 and 2. So what's our strategy? Well, just like we did with functions of a single variable, we're going to find the value of f for all the critical points in the region. And then we're going to find the absolute max and min of f on each boundary part. And then we'll choose the largest as our absolute max and the smallest as our absolute min. And again, we don't really care if the critical points are local mins or local maxes. We're just going to find the function value and choose the largest for the absolute max, the smallest for the absolute min. All right, so let's implement our strategy. I'll need to find the critical points, which means I'll first find the partial derivatives. Then I'll set those equal to 0. Now when I set those equal to 0, I get a system of equations. It's a very simple system of equation to solve. And we'll find that the solution is x equals 4 and y equals 1. Those are the coordinates of our critical point. So let's evaluate the function at that critical point, and we get a function value of -10. Now we got to look on the boundary. So here's our region. Again, this is our rectangle. X is going from 0 to 8. Y goes from -2 to 2. So there's 4 sides to it. There's 4 parts to the boundary. And so I'm going to call them line 1, line 2, line 3, and line 4. So let's find the absolute max and min on each one of those boundary lines, starting with line 1. Well, line 1 is the line x equals 0, but only for the interval where y goes from -2 to +2. So if I replace x with 0 in my function here, all of the terms with an x are going to drop out, and I'll be left with a function of y only. I'll call that g of y, and its formula is 2y squared plus 4y. So now I'm left with a calculus 1 problem. I've got a function of a single variable on a closed interval from -2 to 2. So I'll use the same method. I'll find any critical numbers by taking the derivative and setting it equal to 0. In this case, I get y equals -1. And then evaluate the function at the critical number and at the endpoints. Then I'll go on to the second line. Again, so what have I done here? I evaluated at the critical numbers and the endpoints. So at the second line is the line y equals 2 over the closed interval 0 is less than or equal to x less than or equal to 8. So if I replace or substitute y with 2 in the formula for my function value, I'll get a function that has only x as a variable. So I'll call that h of x, and its formula is going to be x squared plus 8 minus 4x minus 6x plus 8. So you see what I've done here? Up here, I replaced y with 2. So 2 squared is 4. 4 times 2 will give me my 8. And then here I replaced y with 2. So instead of having minus 2xy, I have minus 4x. And then instead of having plus 4y, I have 4 times 2 gives me plus 8. So I can simplify that. And now I've got another Calc 1 type problem. I have a function of a single variable over a closed interval, and I'd like to find its absolute max and absolute min. So first, find any critical numbers. There's only one, x equals 5, and then evaluate this h function at the critical number, and then at each of the endpoints. Now notice there's a little bit of redundant work here because h of 0 corresponds to the upper left-hand corner of my rectangle R. That's the same as g of 2. So sometimes we can take a shortcut and take advantage of that, but I'm going to work it out so that I have a sanity check. H of 0 and g of 2 should be the same, and that gives me confidence that I did not make an arithmetic or a silly algebra error somewhere before. Well, let's move on to the third line. Now I think we've got the idea. X will equal 8, and the y range will go from -2 to +2. So again, I'm going to put 8 in place of x in my formula here. And I went ahead and simplified that. And I'll get a function of y only. I'll call that k of y. And it has the formula 2y squared minus 12y plus 16. Now, if I take the derivative there, set it equal to 0, I get y equals 3. Well, y equals 3 is not in my boundary. So when I first worked this problem out, I went ahead and blindly evaluated it. It didn't really hurt anything because it wasn't one of the absolute max or min, but really you should not even evaluate it because it's not between -2 and +2. I still need to find the values at the endpoints. So k of -2 is 48 and k of 2 equals 0. So k of 2 should be the same as h of 8, and it is. So that's good. So our last line here, we have y equals -2. X ranges from 0 to 8. So if I replace y with -2, I get the function x squared minus 2x, a function of only one variable, and I call that p of x. So I find its critical number, x equals 1, and then find the values of p at 1 and at the endpoints. So again, p of 0 should be the same as g of -2, and they're the same. Both of those are 0. P of 8 should be the same as k of -2, and they are both 48. So we feel good about that. We've got some confidence that we got the right values. So now I just have to go through and look at all of the ones that I should consider, not the one k at k of 3, and look at which one is the largest and which one is the smallest. I recommend that on your region, if you can draw a plot when you have so many values, that you go ahead and write the z values. So like here at this corner, at 0, 2, the z value is 16. This was our critical point, which was what? At 4, 1, z was -10. Here at, this was g of 5, right? Or h of 5, I'm sorry, h of 5, the z value is -9. At this corner, it's 0. Down here, it's 48. At this value, it's -1. Here, it's 0. And here is -2. And so that can also help you maybe get a handle on what the surface looks like and give you a sense of if all of these values um, are reasonable. And amongst all of these, the largest one is the one at this corner, the lower right-hand corner where z equals 48. And the smallest one is at our critical point where z equals -10. So my absolute min is -10 and the absolute max is 48. All right, got a second example. Here we have a simpler function. We just have f of x comma y equals 2x plus 2y plus 4. But now instead of having a rectangle as our region, we have a disk. It is just the closed unit circle or unit disk. So when I take my partial derivatives, they're constants, which will never be 0, so there's no critical point. And this makes sense because my function here, it's a surface which is a plane. Z equals 2x plus 2y plus 4 represents a plane. And a plane does not have any local maxima or minima. But what about the boundary? I don't have any boundary lines per se. I have a curve. But it's the unit circle. And when we were studying curves, we learned the parameterization for the unit circle. A simple one is to just use x equals cosine of t and y equals sine of t. That's because cosine squared t plus sine squared t equals 1, and we want x squared plus y squared to equal 1. So now if I go back to the equation of the plane and I replace x with cosine of t and y with sine of t, I get a function which only has one variable t. And what does t range from? Well, I go around the circle once, so t goes from 0 to 2 pi. So now I have another calculus 1 problem. So I'm going to find any critical numbers. So I'll take the derivative. I'll set that equal to 0. When I solve that, I'm going to get tangent of t equals 1. And tangent of t equals 1 between 0 and 2 pi when t equals pi over 4 and 5 pi over 4. So once in the first quadrant, once in the third quadrant. All right, so on my endpoints, when t equals 0 and t equals 2 pi, my z value, so the value of g, is going to be 6. If I put in 0, cosine of 0 is 1, but sine of 0 is 0. So I get 2 plus 4, which gives me 6. Now, at the critical numbers, well, at pi over 4, I'll have cosine and sine are both root 2 over 2. If I multiply that by 2, I get root 2. But then there's 2 of them, so I get 2 root 2 plus 4. At 5 pi over 4, sine of 5 pi over 4 and cosine of 5 pi over 4 are both negative root 2 over 2. So I'll get negative 2 root 2 plus 4. Now, it looks like the largest of those is going to be 4 plus 2 root 2. The smallest is 4 minus 2 root 2. And here's the picture of this particular problem. We have this plane. Here is, well, really, I could think about we're going over the unit circle, so I really want to look at the part of the plane where the cylinder, based on the unit circle, intersects the plane. That's going to be a curve, and it's going to have, on the curve, there's going to be a high point and a low point corresponding to our absolute max and absolute min. Our third example is similar to the second example, but we still have a plane, but we're going to take it over an ellipse, a closed ellipse. And I see that there's just a missing y here, so let me just fill that in quickly. There we go. So let's go through our method. Again, if I take the partials, I get constants. We've got a plane. There's no critical numbers there. So let's move on. We're going to rewrite the equation of the ellipse. So I've got to work on the boundary here, which is the boundary of the ellipse. So I'm going to divide every term by 4 so that it equals 1. Why do I do that? Because I'm thinking about my Pythagorean identity, that cosine squared t plus sine squared t does not equal 0. It equals 1. That's funny. Oops. There we go. All right. So if we've got that Pythagorean identity, then what do we want to do? I have to put a 1 over that. Well, the way I've written this, then this would say x squared plus quantity y over radical 2 squared equals 1. So the natural thing would be to say, oh, okay, well, x should be cosine of t, y over radical 2 should be sine t. And that would mean that, of course, y would be radical 2 sine of t. All right, so now replace x with cosine of t, y with radical 2 sine of t. In the equation of the plane, I'll get a function of only one variable. Trying to make this correction here. And I'll call that g of t. So now, and t ranges from 0 to pi over 2. So now we have our calculus 1 problem. We'll find the critical numbers and evaluate at the boundary. So I'm going to go ahead and evaluate it at the endpoints. Evaluate at the endpoints. So g of 0 is the same as g of 2 pi, which is just going to be 7. All right. Take the derivative, set that equal to 0. And now I get an equation where I don't see a simple way of proceeding uh, in this form. And there might be, and if you find one, please let me know. But another way that we could proceed to find the absolute max and the absolute min on the boundary, is to switch back to x and y. Sine of t is y over radical 2, and cosine of t is just x. So we have this relationship between y and x, which I can simplify as y equals 4x. And then I can take this relationship here and I can substitute that back into the equation of the ellipse. So let me just make my correction here real quick. I apologize. I proofread these things, but it just seems like I always get into trouble. All right, so replacing y with 4x in the equation for the ellipse, that's going to get me a simple equation involving only x, which I can proceed to solve and find two values, x equals plus or minus 1/3. Since y equals 4x, that would mean that y equals plus or minus 4/3. And so my function value at 1/3 comma 4/3, again, I'm going back to now the function value, equation of the ellipse, will turn out to be exactly 9. At the other extreme value for on the boundary, where x equals negative 1/3 and y equals negative 4/3, I get a function value of 3. And so those are, the endpoints don't come into play here. They rarely do, but you still should evaluate it. So our absolute max then is 9, and our absolute min is 3. So last example. Here we have a large rectangular plate, and it's heated so that its temperature at a given point can be found by evaluating T of x comma y equals 360 times e raised to the power of negative x squared minus y squared. And our job is to find the hottest and the coldest points in the triangular region with vertices negative 2 comma 0, negative 2 comma 2, and 0 comma 2. So there's our region. Let's see if we have any critical numbers to deal with. I'll take the partials. I'll set them equal to 0. And that has a solution where x equals 0 and y equals 0. But 0 comma 0 is not in this triangular region. So I'm not going to consider it. Now let's go through the boundaries. I've got 3 lines that I've called L1, L2, and L3. And we did this in a previous example, so we're going to do it again. The first two we'll go through pretty quickly. The first one is where x equals negative 2 and y ranges from 0 to 2. So when I put negative 2 in the place of x, I get a function of y only. And so I will go ahead, take the derivative, set that equal to 0. my critical number turns out to be one of the endpoints, so I only need to evaluate this g function at 0 and at 2. And in the second line, this horizontal line, I'm going to see something similar happening. Now I replace y with 2. I get a function of x only, which I call h of x. I take its derivative and set it equal to 0. And that gives me x equals to 0, which again is one of my endpoints. So I only need to evaluate this at x equals 0 and x equals negative 2. Now, the third line is more interesting because it's a slanting line or a sloping line. It has an equation y equals x plus 2, and the x values range from -2 to 0. So now, instead of replacing y with a constant, I'm going to replace y with the formula x plus 2. So after I do that and simplify, I have a function of only one variable, x, and I'll call that function p of x. So now when I take the derivative of p of x, set that equal to 0, I'm going to find that x equals -1. And when x equals -1, y equals 1. I'm actually at this point right here on the boundary. And so now I have to evaluate p at the critical number, -1. And I should also do it at the endpoints, but I already did it. So here's a case where if I looked at um, p of 0, that should be the same as g of 0. And if I looked at p of 2, that's the same as h of 0. All right, so now I've got all my temperatures on this region to consider. So the critical point did not come into play. On the first boundary, I only looked at the endpoints. I had 360 over e to the power of 4, 360 over e to the power of 8. On the second line, 360 over e to the power of 4, that's good, that should match up. 360 over power of 8 at h of -2. Oh, I'm sorry, that doesn't have to add up. It's these two that have to match. At any rate, the highest temperature is on the slanted line here at that critical value, the critical number, x equals -1, 360 over e squared. And then if I look among the other ones, the coldest point, or the coldest temperature, is 360 over e to the power of 8. And that occurs at the point when x equals -2 and y equals 2.